AMUG, 3 p.m. Kind of a tough time slot, but we're glad that you're with us. I'm Zach Murphy. I'm VP of Technology Partnerships at VELO3D, and I'm presenting today with Scott Volk, CTO of Encodema 3D. And today we're going to talk a little bit about some of the challenges of taking parts into production with metal additive manufacturing. So with that, I'm going to let Scott go ahead and introduce his company and run through some of the challenges associated with that.
Hey guys. Hey, really want to thank everybody for showing up. I know it's a bit of a challenge to hang around and be here on the last day, especially AMUG, after it's a pretty involved event and pretty worn out by this time. So really appreciate you guys all showing up and being here for this. Encodema 3D, we've been around for a few years now, incorporated in 2014. Before that, we were actually working. We just were working on how we wanted to be before that. So there's almost 2 years before this that we were hiding behind the scenes before we came out and incorporated ourselves. Myself, I've been in the industry for 25 years, so I bring quite a bit of experience to this business. I think next year it's finally half and half now, so I've got just as much plastics experience as I do metals experience, so I'm finally at that mark. I'm really primarily focused on metals now, and specifically laser powder bed fusion. So that's what we do at Encodema 3D, is laser powder bed fusion. We're a manufacturer using AM technology. We have all internal machining, finishing, and we've got a fleet now of 19 machines that we have on the floor, ranging from our Renishaw AM400. We have a couple of Pro X 320s, and then most of our fleet is EOS, ranging from 280s, 290s. We have several 401s and a 404 as well. So pretty diverse fleet of machines. We can really work within just about any application you're looking for. Today, some of the things that we're talking about is the challenges that we run into as we're trying to qualify production work. And that's the reason, even with our whole fleet as it is, there's still some challenges that we run into. And a lot of it is, how do you qualify these machines? When we're looking at some of the specifications that are starting to be developed and as they evolve, there's a lot of questions that we end up running into. And I like to say these are the questions that keep us all up at night, or at least they keep me up at night. So there's things that we run into all the time. Some of these specifications, for instance, there's a specification out there that says any interrupted builds or unscheduled stops within a machine is a failure. It's no good. You can't continue it. You can't do anything further with it. So that's a big problem, especially when a lot of these builds, we're running into 85 hours up to 200 hours. It really depends. And unfortunately, the way these machines work, we're usually at about the 195th hour of a 200-hour build, and that's where it fails. And so we just can't afford to have those kind of things happen when they're non-recoverable. So one of those things is, do we have enough powder in the machine? Anybody in here who's actually run machines knows, the way to get past short feeds is to overcompensate and feed enough powder so that you don't have short feeds. Well, the flip side of that is then you don't have enough powder in the machine to run your entire build, so you're riding this fine line all the time. So we really need some assistance from the equipment itself to manage itself and understand how much powder is in there, how do we know that, and right now, currently, the sensors for that are challenging. So it's one of the things about this system that excites me is Velo's really put a lot of energy into this kind of monitoring and understanding how that works. Inconsistent airflow. If you look at all the different equipment that's available today, they're all pretty much different, and every one of them's got some sort of situation where the airflow, you have a situation on this side of the build or that side of the build or up here or over there. There's a few who have focused on laminar flow, but I'm not even sure laminar flow is the answer. It's what we really want is all parts building consistently across the entire bed. And depending upon your laser scan strategies and how the equipment's built, that varies from system to system. Controlled atmosphere. We have different levels of oxygen across all different equipment. And a lot of times, what's the sensors like? How do we know what we're reading? Many of them read in percentages, many of them read in parts per million, and then how sensitive is that? How accurate is that? And then, of course, in characterization, we're trying to figure out what's the difference. Does it really matter? How much does it matter? Things like that as well. But until we can actually control it and understand it and monitor it properly, it's a challenge. The lens window cleaning, this actually goes to your control of your process, but it'd be nice if the machines could tell us how well did we do. From operator to operator, from procedure to company to company, and all the different procedures of how lens cleaning is handled. If it's not done properly, and you could look at a lens by eye, you could look at these lens covers and it looks clean, but it may not be. And so this is one of the variables that you can look at that tells you sometimes you get a good part, sometimes you don't, sometimes the machine builds the part fine, sometimes it doesn't. This is actually one of the variables that could lean towards why that happens. And it'd be nice if the system could tell you, as it's building, how well we're doing on that lens window, and is it clean, is it still clean, is it affecting the build? So these are some of the things, again, that Velo has taken a lot of time to look into, and it excites me because I face these challenges on a daily basis. Laser calibration. This is a big question for anybody in here who's actually spent any time around the ASTM. You're going to run into this question. This is where, how do we calibrate these systems? I mean, how do we validate it? How do we verify it? When you're building your parts, part to part, build to build, how do we know that these machines are actually calibrated? In the instance of like EOS, they have to actually come and calibrate your machine. So how long do you go between calibrations? And what's the drift like in between those calibrations? It's really very difficult to validate that thing, that item within your system. This gets much bigger of a problem when you go into multi-laser systems. So like on a 404, for instance, when you're building across the regions, if all lasers aren't calibrated perfectly with each other, there are certain geometries you can't build across those regions because the calibration really matters a lot. So understanding how that calibration is being done and how accurate it is, build to build, not over a time frame, but build to build is very important. And again, Velo has spent some really good time and ability in their semiconductor understanding to put that in the system and understand how calibration works and keeping it under control. This is a big area. Manual review of the imaging, the powder bed imaging. So, melt pool systems, you have, there's several aftermarket systems that you can put in to measure the laser and what it's doing to the part bed. The issue with that, though, is there's really not a whole lot available today that helps you analyze that data. So how do you draw conclusions to the data you're looking at and what it means in my part? Now, if you have the luxury of running some production and you're working through several builds and you have enough time to gather data, you can start to draw conclusions, but many times that's pretty late. We don't have time to do a whole lot of development and understand and correlate all that data ahead of time because everybody's in a pretty big hurry in trying to use additive for production. So this is a challenge. Velo has really put some good time into this, and they do have some really good understanding of, within their own system, having the system in the ability to do that in system and help you analyze that through. And that's a lot of what Zach's going to talk about later. And then we come to the recoders. And keep in mind, this list is a really short list. I just grabbed a few things to point out just to get us started and give Velo a chance to show off what they have going on. There's some really it's a big list of questions that you start to develop as you look at any of the equipment in this side of the industry. But zero tolerance recoder, several of the systems that are out there, it's a real challenge in orientation and understanding how warpage or support structure, and there's a lot of work that goes into that, pre-design into your parts. But this is a big challenge, and again, going back to the zero tolerance of a failed build. I mean, any stoppage. I mean, there are some instances where machines stop for almost no reason. Once you analyze it, you'll understand what it is, but it seems like there's no reason. Well, recoder is a big reason why machines stop, and there's a lot of pre-work that goes into that. And so VELO's really come up with a unique way to handle that situation as well, and it's a lot of the excitement that I have for this. So one of the things just to put out there, you know, in VELO3D almost a year ago, we entered into a MOU with VELO. We don't yet have a system on our floor, but what we're doing is we're working together with them, with our customers, to develop applications and an understanding of how to qualify this equipment and use this equipment for production. So as we're doing that, we're working through these lists, and we really feel there's a really good opportunity here for a new piece of equipment that's going to help us answer those questions that keep us up at night. So with that, I'm going to let Zach take over and walk you guys through what makes us excited. Thanks.
So I think, you know, we really, as a company, agree with what Scott has said here, which is that it can be very difficult to take apart into production, especially on a metal additive system. And there's a lot that goes into a mature production manufacturing system that's really not addressed by some of the conventional additive manufacturing systems. I think that even the latest generation of metal additive systems kind of tries to address the production readiness aspect by really looking at it through the lens of cost. So what you see in a lot of the systems is that they've added more lasers or added a larger powder bed, and the goal here is really to drive the cost down and to drive more parts into production with that focus. But at the same time, you're not doing necessarily enough on kind of the other aspects of the system to really make a production-focused system. It is the parts end up being cheaper, which is a good thing, and that's something that additive needs to focus on definitely. But there's a lot more that goes into a mature manufacturing system that needs to be addressed as well. So I think one of the fun things that I got to do when I joined VELO was kind of ask the question, if you could build a metal additive system from scratch for production, with production as the focus, what would you build, right? And when we kind of started on this journey of building the systems and the software 3 years ago, that was really what we were looking to do. So we set out to address a lot of the kind of shortcomings of some of the existing equipment, so that at the end of the day we would have a system that is really a production-focused system. And I think one of the things that we were able to do was really leverage VELO's experience in semiconductors, Scott alluded to, and something that I'll talk to a little bit more later in the presentation, to make sure that we had a process and the hardware and software to actually implement this process that was really a production focus. So one of the most obvious limitations of metal additive manufacturing is supports. And you have to deal with supports if you're printing parts in metal. And this kind of, it limits the applications where metal additive can be a really cost-effective solution. So one of the first things that we wanted to address was to eliminate or dramatically reduce the amount of support material required to build parts in a cost-effective manner. And really what this involved was looking at the process that exists and kind of redesigning it to build some of these lower angles and eliminate the supports. One of the things that this required was to take the process window that exists on conventional additive equipment and shrink it by a lot. Because if you're operating in regions where traditionally you need a lot of support material and you're trying to build that without supports, you really need to have some pretty precise process control to do so successfully. Fortunately, VELO had built a team of people who had a lot of experience in working with processes that needed a lot of control. And really, this comes from the semiconductor heritage of VELO3D. So the vast majority of the people that worked at VELO3D at the time were from semiconductor capital equipment or process development, and they were used to working in situations where the process is king. And everything that you do is to enable that process. So at VELO3D, we really took this process that we had developed and then built everything around it that we needed to build in order to make it successful. And that's how we started off building the VELO3D Sapphire system, the printer that you see on the left, and then the Flow software which is our print preparation software that you see on the right. And all these things together form a pretty tightly integrated system that really is focused purely on production. And so enabling the process was definitely a key focus, but there was a lot that came with it that I think will help to move metal additive further along the kind of production maturity. So you may have heard us talk about support-free manufacturing, and I think it's useful to give kind of an idea of what we mean by support-free manufacturing. So in metal additive, there's kind of the standard 45-degree rule, which is overhangs that are 45 degrees or lower from the build plate generally need supports. And people have done a lot of work to push this to lower angles, and you see, depending on material and geometry, people pushing this to lower angles. But there's still a lot of limitations around what can be printed and what supports you can actually eliminate. So VELO3D's support-free process is what we've developed to basically eliminate supports down to around the 5 to 10 degree range, especially depending on the geometry. So we are able to print parts, and I don't know if you guys had a chance to come by our booth. We have several examples of parts that we've printed that have 10 degree overhangs with very good surface finish on the bottom without supports. And I think it's pretty exciting because there are a lot of applications that seem like they should be really good candidates for metal additive manufacturing that we just haven't been able to pull into the additive workflow because the supports and the post-processing that goes along with it makes it so that it's not a cost-effective way to make these parts. Shrouded impellers are a really good example of this for us. This is one of our wheelhouse parts, and it's a really good place to eliminate supports. You can make the part that in conventional is challenging and in additive is extremely challenging, and with the VELO system with support-free manufacturing, make it relatively straightforwardly. The printer itself is it's a big black box. We have a 315 millimeter diameter build plate, so it's kind of a large, medium-sized build plate. 400 millimeter Z height. That's true Z height, so you can print a part that's 400 millimeters tall. It's a dual 1 kilowatt system, so quite a bit of laser power for the system size. And I think there's a lot of kind of the specs that I can go over, but really what I wanted to say here is that the system is built with a focus on quality and consistency, because these are some of the things that makes it challenging to transition to production, right? You have variability in properties and outcomes, and we really wanted to make sure that we were making a system that that reduces the variability by a huge amount. And part of that was relying on the semiconductor background and building in metrology that you would have in kind of semiconductor grade tools to make sure that the process is running nominally, that the system is performing how you want it to, and that the outcomes are consistent, not only within a build and across multiple builds, but machine to machine. So you have kind of a tool matching goal here with the metrology as well. One other thing that's a pretty unique feature of the VELO Sapphire is that we have closed loop melt pool control. So as a consequence of the metrology that we've built into the system, we're able to actually monitor thermal emissions from the melt pool and respond to them in real time so that we have a process that is actually running in control, in active control. That allows us to do some pretty neat things, especially with very challenging geometries. We have other metrology that helps us around some of the failure mechanism monitoring. So Scott kind of alluded to some of the powder bed monitoring that we have. We have a height mapping system that gives quantitative, basically scans of the powder bed before and after recoating. We have protrusion detection. There's a lot of metrology that's built in, not just on the melt pool side, that allows you to have, to implement a really robust SPC, statistical process control, on the system and across a fleet of systems, hopefully. And then the non-contact recoder is also a pretty unique aspect of the system. So this is a recoder that doesn't actually touch the build plane, and allows you to not only build these very low angle overhangs, but if you came by our booth or if you've seen some of the videos that we have on our website, it lets you print parts free floating in the powder. So depending on the geometry, you can start a part in the powder and build off of essentially that point. We have a really, if you get a chance, down in the booth we have a 11-inch tall model of the Boom Aerospace XB1, their demonstration supersonic plane, that we printed free floating in the powder. It was just standing on its nose, 11 inches tall. It's a pretty neat It's an Inconel lawn dart. It's kind of a dangerous model, but it looks cool. The software side is also really exciting for us. And what we've done is build a print preparation software because we weren't able to leverage some of the existing third-party softwares to really implement our process and some of the simulations that we built into this system. So Flow is our print preparation software. We take direct CAD import. We are trying, and I hope everybody else is also trying, to not use STLs. If you're not, we can talk about it later, but we take in CAD import, so you have kind of the NURBS representation. It's a higher fidelity representation than a tessellated file, and it's much easier to work with in this software. So import a part, you kind of can do standard orientation and supporting, but then we have some kind of unique capabilities around simulation, where we built an in-house solver that allows us to do deformation correction of the parts. So we can pre-deform the part, and what you print is actually what you intended to get out of the machine rather than something that warped into a different shape during the build. The simulation also allows us to predict failures. So if you have an under-supported part that's going to deform, or if you have supports that will be under too much stress and will fail, the simulation can inform you that this is going to happen, and you can modify orientation or support so that you don't get 3/4 of the way through a 12-inch tall print before you realize that something wasn't supported well enough. And that helps us with kind of the first yield success. The other thing that I really like as a designer is that we've kind of changed the way that you can apply processes in the software. And the way that I like to think about it is, as a mechanical engineer, you have a machine drawing. And the machine drawing is kind of your map of design intent, right? So you have a part, and it has surfaces, and you have callouts on dimensionality, you have callouts on surface finish, and this gets at kind of what you're trying to accomplish with the part. One of the things that I think is not easy to do in some of the existing software is to have that same kind of mentality when you're setting up a build. So the feature that I love about the flow preparation software is I can take a part and say, the stator ring that you see on the screen. I can say, okay, the outer hub and the inner hub, I know that I'm going to machine because I need to have those be mating surfaces in an assembly. So I'm going to select those surfaces and say, I don't care about surface finish, right? And then I'm going to select the airfoils, the parts that are yellow in the picture that you see here, and say on these parts, I really care about surface finish. These are fluid interaction parts. The surface finish is critical. So I'm going to select those and say, this should be a high quality surface. And then everything else on the part I'm going to leave as standard. So it's kind of a compromise between throughput and speed. And in doing this, you basically kind of input the design intent into the print preparation so that the instructions that it generates for the machine leverage that. And it basically will turn off contours on the outside and inside hub so they print more quickly. It will do a higher quality process that gives you a little bit of a throughput hit on the airfoils, but gives you the design intent that you want, the very smooth surface. And then everywhere else you have kind of a compromise between throughput and surface finish. And the nice thing is that it does this all automatically, so you don't have to take a file and slice it up into multiple Z heights and pull parts out of it and then apply different global parameters to it and reassemble it and hope that everything went well. This is really a very intuitive way to translate your design intent into file preparation. So it makes my life easier. And all of these things together are what enable printing of really kind of novel geometries, parts that should be good candidates for additive, but really haven't been kind of fully taken advantage of yet. So whether it's parts for gas turbines or pumps, turbo pumps, compressors, we have a lot of impellers and volutes that we can print that on other systems would require supporting, that makes it basically uneconomical to approach. Heat exchangers. So this part is one that I like a lot because I designed it. But other than that, it's also a really cool demonstration of the non-contact recoder. It's a 6-inch tall part. It has 250 micron thick walls, so 10 thou thick walls that are at every angle. It's radial walls. So one of the things that you may have experienced with some of the conventional recoders is that if you have thin walls that end up being parallel to your recoder blade, when you go to recoat, bad things can happen. And with a non-contact recoder, this isn't an issue anymore. So you can print these high aspect ratio structures in any orientation and kind of not worry about whether or not your parts are square to the recoder. So we print a lot of really cool parts. And the question that we always get asked by customers is, these are nice geometries, but is it real metal, right? Are you actually printing high quality material? And I'm presenting this data here because I think one of the things that we need to do better as an industry is present this kind of data in a way that's more meaningful to the designer, right? So if I have a material sheet and it calls out a mean value for the ultimate yield or the ultimate tensile strength for 718, that's great, but that doesn't help me. Because if my variation is, if my mean minus 3 sigma is half that, then my design allowables are shot. So I wanted to present some true statistical data from our standard parameter set around at least static mechanical properties. And the thing that we're excited about here is not that we're printing material that meets ASTM F3055 spec, it's that we have a pretty good reduction in the variation of the mechanical properties. And elongation is kind of the one that we consider critical, because this is kind of our canary in a coal mine for mechanical properties. Your elongation is the first thing to suffer, at least in our experience, from process excursions. So having a mean minus 3 sigma on elongation that is well above spec is something that will be very useful to designers at the end of the day. In addition to static mechanicals, one of the things that people always ask about is surface finish, especially with 3D printed parts. And another thing that drives me crazy about a lot of the material data sheets that you'll get is the surface finish callout will say 6 micron RA. And it's like, where? Like on what part of the part are you getting 6 micron RA? Is it everywhere? Is it every surface? What angle is it at? What's your variation? So we wanted to kind of give an idea with a base parameter set. These are surface finishes that we're measuring. So statistical significance on actual measurements with assay. We measure an assay because we consider it to be a better measurement of surface finish, because with RA it depends on which direction you're scanning. If you scan across layers, you can get a much different RA than if you scan with layers. So assay somewhat accounts for that, and at least you won't be surprised by the part you get out of the machine at the end of the day if this is the data that you get up front.
Is this generally material independent, or?
Sorry, no, this is 718. Yeah.
Okay.
Yeah.
Thank you.
We do 2 materials. We do 718 and Ti 6.4. And we have a material roadmap to expand on that. And if you have strong demand for something else, we're happy to hear it. But this data, the data that I'm presenting here is all 718.
Okay.
So one of the other aspects which Scott was talking about was kind of the optics system. And when you are looking at a metal additive, especially a laser powder bed system, the optics is the heart of the system, right? It is what makes or breaks what you're doing, really and truly. And having an executive team that's very steeped in the metrology and semiconductor, they wanted to make absolutely sure that we're able to characterize the optical health live, right? There should never be a question of whether your optics are performing nominally. So we built a lot of metrology and sensing into the system around this. And I'm going to go through a couple of slides here. Bear with me, we couldn't bring a system, it wouldn't fit in the room. So I have screenshots of our actual build GUI. So this is from the machine. This is a machine that was running in our facility. And this is from the production system. There are a lot of things that you need to be aware of in the optics system to get good parts out at the end of the day. One of the really critical ones is laser alignment. And as these machines push to more and more lasers and try to get costs down by driving throughput up with multiple lasers, you really have to start worrying about laser alignment, especially if you're building a big part with multiple lasers. And that's a difficult thing to do. And a lot of times people are doing 3 to 6 month PMs to do laser alignment. And between that time, you may not know what's going on. And the one true thing I can say about galvos is galvos drift. And the calibration drifts. If the temperature changes in the chamber by 10 degrees C, your laser alignment's shot, unless you have a way of measuring it and correcting it real time. So that was one of the things that we built in. We can calibrate the laser alignment to each other, and the distortion, what we call the distortion quality, which is basically a measure of the Cartesian mapping of the galvos. And we can do this live. So This is a screenshot of before, well, this is actually during a build. You can see that it's building. You can do your optical alignment and calibration before the build. It takes about 3 minutes. And then during the build, as a configuration, you can set the machine up to check this every so often, right? Every 50 layers, I want it to check and make sure that everything's still in spec. And this is really important if you're doing super tall builds because the galvos tend to drift in time. So if you have a 6-day build, you don't want on the 6th day for your galvos to start to diverge and for your stitching to turn into garbage. So this is a really useful tool, and we've seen some really good results from being able to do this in situ. As an example, this is not a super rich example, but you have a couple of blocks that we printed in the upper left. And you can see when you have galvo misalignment, you have kind of this is in Z, so it's a little bit different than a traditional stitch line. But this is basically an offset due to laser misalignment. If we turn on the calibration, you can see kind of the plot of what the calibration is doing in the bottom. So in this case, we're doing it every layer, which probably is overkill. But the system can basically start to correct itself and make sure that you're staying in a nominal band. So you set an upper and lower control limit, you start running the system, turn on the automatic calibration, and the system makes sure that it is printing nominally. And this is really, really kind of a different way of approaching it than a lot of kind of the traditional metal AM systems. Another big one, which Scott mentioned, was the thermal lensing. So how clean your optics are in essence. If your optics get dirty, the laser will hit the dirt often and will start to heat up locally the optics. You get an index of refraction change and your spot size changes. And when your spot size changes, the energy density delivered to the plate changes. And you can get some pretty nasty porosity effects if your spot size is not consistent. So we've built into the system the ability for it to actually measure the spot size and to attribute that to causes. And one of them is thermal lensing. So we can measure the thermal lensing live during the build, again, at any point during the build. This is not actionable by the machine because if your window's dirty, the machine's not going to clean its own window. But this is something that we find changes over long time scales. And one of the reasons this changes over long time scales is that we've developed optics purge system, essentially, that means that we only clean our windows every 3 to 4 months. So we don't clean our windows every build, and that's not something that we think you should have to do because it's a procedural, it's a opportunity for procedural mishaps. And if it does happen, you won't know until the end of your build. So we run 3 to 4 months in between cleans, and the reason we have confidence in that is that we have the measurement to back up the fact that there is no thermal lensing occurring. So once you hit a control band, you can give a warning to an operator, say, okay, 3 months is up, let's clean the window. Clean the window, check to make sure that the window is clean with the system itself, and then keep printing. And all this is well and good as long as you trust your sensors. And that's a really big part of this. You can't do closed loop control, you can't do these laser measurements and calibrations in situ unless you have a really robust sensor and it's characterized. So the system also can make sure that the sensor that you're using to do all these measurements is essentially self-calibrated. So we can make sure that it's aligned with what it needs to be aligned with, and that your intensity is good, that your signal width is good, and that you can trust the output of the sensor. So that's kind of a critical part of this that you wanna also be tracking in time. This is really the same data that I just presented, but this is kind of our overall screenshot. And one of the nice things about the system is that it's reporting all this stuff, and you know when it's last updated, you know actually the user that updated it. We have RFID control on the system, so you can't just walk up to the machine and start pushing buttons. You have to log in, and every action is logged. So I hope you're pushing the right buttons. But we have complete traceability of the calibration of the system, which I hope is really useful in getting these systems to be qualified much more rapidly in production. Over on the left-hand side too, we have kind of our measurements that are of use, and these are always reported live. This is configurable, so you can change which sensors appear on the UI while the system's running. Generally, we're running at less than 1 ppm oxygen, which is pretty good. One of the reasons we're able to do that is that the people who designed our system are used to designing systems that are full of selenium and arsenic, and you want to keep those gases in and the other gases out. So they designed a very pressure-tight system where you can get to these very low oxygen levels and operate there. Another thing that we have here is humidity. That's something that is being talked about more and more, and it's something that should be tracked because it can be a root cause of failures. We'll see if this works. This is a video in PowerPoint, so the odds are not good. Hey, so this is a preview. This is not defect detection, but this is thermal data from the build. So this is kind of the thermal signal that we're collecting during the build, essentially kind of a virtual CT of the thermal data. And this isn't novel. There are a lot of companies that have this on the system. I think the thing that we're working on that we're super excited about and that we should be launching later this year is a real high correlation prediction of defects, of lack of fusion defects and surface defects that you could get from this data. And I know that this is kind of, everybody is trying to get to this point, and until I can prove this, I'm not going to show anything in more detail. But we have a very strong correlation across a number of sensors that leads us to believe that we can actually give a really good indication of the defects live during the build. And we're really excited about it. Again, take it with a grain of salt now. This is not proof of that by any means. But this is kind of the foundational groundwork that we need to do this. And we're getting really close. So we're pretty excited. Just to go back a little bit to what Scott was saying, and maybe provide a little bit more specific color around the individual points that he highlighted. Full pipe, full build powder. So we have in the system, this is kind of a system spec, so it may not be quite as interesting, but we have 2 full builds worth of powder. There's no overflow in the system, so you don't have to worry about overdosing. We have hot addition of powder, so you can add powder live during the build. The gas flow uniformity is actually validated through the process metrology, not just through CFD. So we know that the process outcomes are consistent based on that metrology. Oxygen level and humidity monitoring comes standard in the system. You saw it reported out on the build GUI. This is part of the build report that you get at the end of a build from our database. Laser window cleaning is much less frequent than what you see in current systems, while laser calibration is much more frequent than what you get in kind of conventional systems due to the automated nature of that. The powder bed imaging, one of the most interesting metrologies that we have is this like 3D scan essentially of the powder bed. So I can report out every layer what's really going on with the powder bed, the quality, the protrusions that you might be seeing. If there's supports that are failing, the system will measure those and actually give you a quantitative measurement of that and not allow the recoder to smash into it, which is a nice feature. And then the protrusion tolerant recoder is another kind of novel thing that, there are a lot of causes for build failures, but the way they tend to manifest themselves is in a recoder crash. And being able to avoid recoder crashes is a good way to make sure that you can get through builds successfully. So that's kind of the summary of the system and what we're trying to work on, and I hope that it's intriguing and kind of the right step towards taking these systems to production. So, thanks. Questions?
I'm not very familiar with the VELO3D, but how do you actually check your laser alignment during the build? Do you have some kind of mechanical device that goes over the build, or how do you actually do it?
It is a method that doesn't cause pauses in builds. So it's kind of a proprietary method to check the alignment, and it is something that can happen very quickly. Sorry, I can't provide more detail on that. Very back.
Were the material properties you showed as built or heat treated?
Oh, yeah.
Heat treated by non-standard?
Yeah, good question. Those were heat treated and hipped. It was a AMS 5662 heat treatment.
Okay.
Yeah.
Was it PSD or the powder you used?
Oh, that's a great question. So this is standard laser powder bed cut. This is a 15 to 45 or 15 to 53 micron powder, gas atomized, plasma atomized. The recoater itself is fairly insensitive to the powder. Flowability is always an issue, right? And our recoater is we think, it seems to be less sensitive to flowability than a lot of the traditional kind of snowplow type recoaters. So, thanks. Yeah.
You go into more detail about the recoating system, the non-contact recoating system? Or also, you know, what happens when you see a protrusion, and do you try to counteract that, or you just say, game over?
So there are certain protrusions that aren't bad. And especially when you're building low angle overhangs, things tend to stick out a little bit more.
Yeah.
So that's one of the reasons we built the recoater, was to tolerate that. If they're not normal, if it's a non-nominal protrusion, then the build will pause,
Okay.
but it can't fix it.
Yeah.
Yeah.
And no details on the mechanism?
Something we talk about under NDA.
Okay.
Are the two lasers full field lasers, or is there an overlap zone?
They can be full field, but we find from a process perspective that getting too far out is not a good thing, so we try to limit them to close to laser normal.
Is there an effect with the reused powder when it comes to the geometry ability that your system has compared to what you see advertised for other systems using either the 718 or 64 as an example? Your capabilities, does that limit the amount of recycling of powder?
We've done internal studies to look at PSD and chemical composition as throughout builds and throughout kind of months of building. We haven't seen a significant deterioration in especially the PSD. So it doesn't seem to be a real issue.
Actually, I'll just add on that one. So this is an area that I'm obviously really concerned about as well. And as he said, the recoder is something they can discuss with you in more detail under NDA. But part of that recoder technology, they treat the powder throughout the build process. So it's not like most other systems where the powder is collecting, and they truly are working with the powder as the build is building. And I do understand this from a lot control. This is something I've been talking to them about, working through. But when you do find out how that recoder works, there is a portion of the process that has to be done this way. But I actually look at it as a way that it actually helps us understand the powder even better. Because really, that question comes into play when we're looking at serial production. So over serial production, because this reuse question comes up a lot. And really it depends on the density of the build. I can go through this, it's not what this intended talk is about, but when you start looking at the density of the build and the hours, there's really very little way to make conclusions on reuse of powder without running serial production. When you run in production, build after build after build of the same exact build, now we can start to make conclusions around how many times can we use that powder, because that's a build, right? But beyond doing that, it's not an easy answer to say, well, 5 times through the machine, because it's not based on hours, it's not based on exposure limits, it's a very complicated situation. In this system, because of the way the powder is being handled, it's much easier to track. You have much better control over the particle distribution, so it's actually a really well-controlled system, and it handles that whole problem in a totally different way. Once it's fully exposed on how the whole system works, I think you guys are going to like how the powder handling is done.
Very
So
good.
you've talked about the shift between lasers in X and Y.
Mhm.
Are you also measuring the rotation and the shift in Z direction?
Yeah, so we, in terms of the rotation, we consider that part of our distortion measurement. So the kind of the Cartesian mapping of the galvos, which is accounted for in the calibration. And then the offset in Z manifests itself as a focus shift, right? It's as a spot size shift. So we also have the ability to check the spot size. We do it in several locations on the build plate live during the build and validate that we're not getting spot size shifts, which is essentially your Z offset. Yep.
Can you vary the spot size actively?
Yes, yeah, absolutely. Yep. It's a dynamic focus. Yep.
Concerning the closed loop measurement, can you say something, how do you make sure that you're doing the right thing in terms of control, and how do you test and consider this valid? It's also obviously difficult, especially if the process window is narrow,
Right.
to really get it to the right point.
So the targets are kind of a robust target for a particular situation, and that's part of the process prescription from the print preparation software, is that you kind of define these thermal profiles for different geometries or different angle ranges. And those are validated through, a lot of process DOEs essentially, what the profile should be and kind of banding it on both sides. We set control limits on the amount of control that can be applied. So, if somehow the laser says, oh, I'm running it at 800 watts and all of a sudden it's telling me I need to be running at 20, like that's not an acceptable change. That's not an acceptable control command. So there's been a lot of work to set bounds on that as well. And this is the control that's applied is one of the things that is reported, because that's one of the questions that, just the term closed loop multiple control scares the hell out of a lot of people. And we recognize that. And the only way that we can make people comfortable with it is through data and through traceability and documentation. So that's something that we're definitely focused on to make sure that people are comfortable with the notion of closed loop control.
So this is another one that I'd like to add to. So we haven't actually made this connection throughout the talk. He did mention, I mentioned, and he talked about that they use simulation ahead of time. So if you're watching the industry right now, you're seeing that there's a lot of talk going on about pre-simulation and distortion correction. It's really important to keep in mind that they're verifying the file ahead of build, and the machine understands the simulation ahead of time. So they're simulating, compensating for that. So when we talk about variable parameters per se throughout the process, understand that that's on a limited use basis anyways. It's really, because we've done the simulation ahead of time, we're compensating against that simulation, and so now we have the optimal parameter sets that are needed for that particular part, as he says, throughout the profile. So it's not just a total control over the part by varying parameters throughout the entire build. There's a lot of pre-work that goes into that the machine fully understands what's happening across the process.
And another important note there is that the closed loop control it doesn't have like full autonomy, right? It's not going to change your scan strategy. It's not going to change the hatch speeds. It's not going to change the fundamental instruction set that's given to the machine. So I think that's really kind of one of the critical things to note is that the print file that you're running is a static golden file, and the system is just making sure that it executes the commands in that file correctly.
So to build on that, you got the feed forward and then you got the closed loop.
Yep.
Is the closed loop near real time? We're moving, these things are fast.
It's real time. Yep. I mean, real time as real time as real time can be.
All right, so it's not like every layer. You're actually trying to do it as real time as you can get.
Yeah. It's not taking the past layer and kind of learning from it and trying to do something different in the current layer. It's adjusting the fluence live.
Okay.
Yep.
Have you looked at fatigue performance?
At fatigue performance? We have looked at fatigue performance. We don't have a huge data set on that, and that's something that we're developing now because we know that it's the next question. So, yeah, absolutely. Yep.
What's the next material you're going to characterize?
It's a good question. Right now it looks like we'll probably go with a 625 as kind of a adjacent material with a good application, especially in the things that we've found ourselves to be good at. There are other nickel superalloys that are also very interesting. And then, you know, on kind of a less adjacent application set, aluminum, some kind of aluminum, hopefully not ALSI tin, but maybe, and kind of going from there. So we're open to be swayed.
How far out is the aluminum? What do you guess?
It depends on how quickly someone with money needs it.
Okay.
We're pushing them pretty hard on them.
It's true.
So we could use some help, but I almost kicked him when he said 625.
I've told you that, right? Yeah, in the back.
Yep. You mentioned about having some very good correlation between the monitoring and the actual, I think, CTV scan data.
Yep.
So, few questions: what size, what type of defect? Are you talking about being able to observe individual singularities, or are you doing this like sort of data comparison, having a golden sample? What is this?
It's a good question. So I don't know that we have all the answers to that right now. So having good correlation doesn't mean that you have a product. And I think that's the important thing, is to make a product that's actually useful at the end of the day, that can take, you know, multi-sensor correlations and be able to package them into something that is useful. And I would be kind of getting a little bit out over my skis if I gave you a more detailed answer, I think, on that. But I think within the next 6 months, we should have a pretty solid product offering that will answer those questions.
I assume you're selling your own powder, but you're not. Is there a way to plug that into the feed forward if you had new powders?
We don't sell our own powder. We don't, that's not a revenue stream that we're trying to monetize.
Okay, so I guess my question then is, with a different powder coming in,
Yep.
how do you correlate for that with the feed forward?
Yep. So right now, the way that we operate is that we have an approved vendor list of powders that we've qualified, and we basically run those internally to make sure that everything, both in, you know, the deformation correction, the feed forward, closed loop control, and the metrologies works well with that powder. And once we know that that works, we add that specific part number to our approved vendor list.
Okay, but there's no way to do like a test build and then use that for correlation to do feed forward? So you do that in-house?
Yeah, no, that's exactly what you do. Yep.
Okay. But it would be done with you guys, not at the customer?
Right.
Okay.
Yeah.
I guess another quick question. Have you done, you know, post-part build scans and correlated those back to the original design, and how far off is it?
You're talking about dimensionality?
Yeah.
We have definitely done that, and I mean, the kind of cop-out answer is it depends on the geometry. But if you have more specific geometries that you're looking at, I think we can give a much better idea of kind of.
Have you seen any particular geometries where it's off?
So geometries that deform a lot can be problematic, and one of the things that is especially difficult, I think, from a prediction standpoint, is buckling. So if you have super thin walls that you're doing interesting things with, you can have some buckling deformations that are not straightforward to predict. So I think that's a challenge that's still outstanding.
That's an area that, you know, I face a lot. At Encoding with 3D, you know, a lot of our work is heat exchanger work. And so we run into that problem quite a bit. You know, thin wall, and then, you know, a top surface and a bottom surface, and so you end up with this buckling. And this actually is one of those areas that's really hard to simulate and compensate for, because you're really stretching and pushing down. So you can't really compensate that geometry, because once it pushes back, it's not what you intended on it to be. But when I look at this and I see some of the results that we're running through, looking at simulation, we're doing a lot. I mean, just like we're working very closely with them, we work very closely with SimulFact as well. And in doing that work, and then just to throw in a little shot there of, you know, we have a proprietary patent on stress management as well. So in our analysis of that stress management patent and how that works, we've done a lot of work at simulation and understanding, you know, what happens on the build plate, what happens to the parts, how can you compensate for that. And one of the things that I liken this to is if you look at like flow process for tooling, so in injection molding, You know, I mean, you could see that as conformal cooling has started to affect that industry, many of the rules that we had for flow and how to handle that have changed. So I really think that as we learn how to use additive and we design for some of these geometries, we're going to learn new design rules and methods. Like, so for instance, like an injection molded piece, you know, we know that you can't put a boss on a flat wall, you know, with a certain size because the sink's going to create, right? So I think as we start to learn the correlations between simulation, compensation, additive, how that affects what different type of work factors we have involved in the parts, we're going to start to understand of how, you know, we're not just putting a consistently, you know, a consistent wall thickness. We may go from a thicker wall at one side, trim down into a thinner wall as we go across that platform, because we're understanding the stresses that are applied to all those pieces so that we don't create a buckling effect. But I don't think we have enough data to do that across the board. But as this industry matures and we learn all the tools that we have available, I think that's what we're going to end up. So.
When you talk to your melt pool monitoring, is it on axis, off axis? Are you photoparameter, CMOS?
No. I mean,
Okay.
there are only certain sensing mechanisms that are fast enough to be able to do it, so you can
Yep, gotcha.
probably
I gotcha.
winnow it down. Yeah.
Okay.
All right. Well, thanks everybody for coming out.